Good afternoon, everyone. My name is Armstrong, and I'm joined with you by
Boyea.
I'm Cory, Boast.
Gavin, Marolla.
Charles, and we are Submitted Visions. Submitted Visions focused on developing a system that combines a 3D printer and a heat system, addressing the need for sustainable material and construction methods while refining printer capabilities and material consistency of geopolymer construction. Our system is designed to create a strong, environmentally friendly foundation to provide a more efficient approach to modern construction techniques. We were tasked with developing a mobile heating system to cure geopolymer, create a closed-loop PID controller, and incorporate SCADA into the GeoHeater on the right-hand side. On the left-hand side, we have the GeoPrinter for 3D printing. We developed a Y-axis, improved printing capabilities, and included a wireless SCADA system.
So, what is fly ash? What is geopolymer? And what is the importance of this? Fly ash is a byproduct of burning coal. It is non-biodegradable, which means it doesn't naturally leave the environment. It's also a microparticle. This means it's very small and it can cause irritation if it's inhaled or ingested. This is a health hazard. So what do we do to mitigate this health risk? Sand and fly ash can be used together to create what's called a geopolymer. This geopolymer is just as, if not even more strong than regular cement-based concrete. It is fire and chemical resistant. It has low permeability and porosity. It cures in way less time than regular cement concrete, and it costs way less over the lifetime. So the GeoPrinter is essentially a 3D printer for this geopolymer concrete. The operator will take a bucket of this geopolymer and pour it into a funnel, and the auger, it's a plastic auger that'll take it through the PVC housing, and it'll pass the geopolymer through these two copper plates. These copper plates are supplied with 20 volts from a transformer, and this induces an effect called ohmic heating, which will reach around 90 degrees Celsius, effectively curing. This allows us to also print vertically. So you may be wondering, what is the purpose of this? Well, concrete printers are currently being used in affordable housing projects and also larger factory builds. And with the non-porous properties of fly ash, this can be used in aquatic projects such as dams.
As for the roles, starting with the GeoPrinter, my responsibility was the Y-axis design and implementation. Gavin's responsibility was the G-code, Marlin, and Marlin's setup and implementation. Chuck's responsibility was the SCADA and the electrical cabinet design and implementation. For the GeoHeater's responsibilities, Matthew's responsibility was the wiring, 3D parts fabrication, and GPC mixing. The Boston's responsibility was the wiring, control box, and frame design and implementation. And Sean's responsibility was the SCADA, ladder logic, and HMI design implementation. As far as the GeoPrinter design implementation, we used two plywood boards measured to be 2 feet by 2 feet with 4 springs in between them to maintain a level printing board. 2 NEMA motors along with threaded rods were used to control the movement of the Y-axis. A containment board was put on top of the Y-axis platform for safety reasons, and parchment paper was put on top of the wood to prevent the geopolymer from sticking with the wood, which was also chosen to reduce adhesion. Starting with our 3D printed parts, we have first our wall brackets. This part was used to maintain a square for the Y-axis frame. For the platform wall bracket, this was used to maintain a square wall for the containment wall on top of the platform. And then we have our stepper motor filling, which was attached to our NEMA 23 motors to help the threaded rods move the Y-axis platform. Then we have our threaded rod brackets. This 2-piece bracket encloses a bearing that the threaded rod goes through, and this attaches to the back wall of our Y-axis frame. Next, we have our back wall brackets, which attaches the threaded rod brackets to our back wall, 2 on each side of the 80-20 pieces. And then we have our Y-axis mount bracket. This is a 2-piece part that encloses a screw nut that goes through our threaded rods and helps essential part of our platform movement.
So we use the firmware called Marolla. This is a software that controls and operates our 3D printer. And it's open source, which means that our group was able to modify it and make any changes to the code as we needed. It is built upon the Arduino platform in the RipRap community, which means that we have a lot of sources and knowledge on the Arduino to help with this. This is what translates our G code into making the printer perform. So what G code is it's a 3D printing program language. We use Inkscape to put a shape into it to get G code out. And once we got that G code, we edited it, we tested it to make sure that it fit within the parameters that we needed. As shown here, we have the G21, which means that all of our units get set into millimeters. We have G28, which is our homing. We have G00 and G01, which is our speeds, as well as all the coordinates in between.
So now we'll be talking about our GeoPrinter SCADA system. It is a simple on-off display of the auger's operational status. We send data using the component shown at the top right there. It's called a Boast D1 Mini. Right now, the SCADA system is very basic, but has the potential for expanded functionality if the need arises. So you'll see a simple flow chart of data transfer here. It begins in the GeoPrinter's control board, which is hardwired to the Boast D1 Mini. So while it is printing, data is sent through the control board to the D1 Mini, and once that is received, it sends the data wirelessly to our MQTT broker, which is housed on the same laptop as our Edition SCADA software. So that broker receives the data, decodes it, and then sends it directly to the SCADA software for operating view. Here you'll see our wiring cabinet, 3D model. It is a wiring cabinet made of laser cut masonite. Here's the finalized design for our cabinet. You'll see on the left side there is the outside view with the LCD display on the front used for manual control of the system as well as viewing the progress status of whichever print that you're running. On the sides you have fans which are used for extra cooling and ventilation. On the rightmost picture you'll see a top-down view of our wiring cabinet, which from top to bottom you can see different components. You have the 12-volt power supply on the top. In the middle there is the Boast D1 Mini circuit mounted onto that acrylic board. Below all of that is the control board for our printer.
All right, GeoHeater designs and development processes. So the top left screen, we have the HMI encased into the control cabinet made of high-impact polystyrene. Encased in that control cabinet is a PLC, power supply, relay, and Ethernet switch. On the right-hand side, we have the heater, and just below is the IR sensor. In the middle, we have the 3D printed heater bracket, the heater bracket adapter to the tripod. And just below that is the IR sensor laser pointer housing and its sister tripod adapter. GeoHeater wiring diagram. So we have a 12-volt, 24-volt control power, double open relay controlling heater power, and IR temperature sensor. The relay acts as a smart switch receiving on and off signal for the PLC. The IR sensor measures the temperature of the surface of the geopolymer without touching the geopolymer itself, since metal binds with geopolymer.
So GeoHeater hardware and software. For the GeoHeater controller, we use a Automation Direct DRX PLC that uses Do More software. And programmed into the Do More software, we have a PID controller that controls the IR sensor and the heater. So the way the PID controller works is it uses 3 control variables of proportional, integral, and derivative that bring the temperature steadily up to a programmed in set point. This is a close-up of the HMI screen that is on the front of the control cabinet. On the left, we have the control side where we can turn the heater on and off, as well as switch screens. On the right, we have the trend view where we can see the temperature, the PWM values, and set point. The tuning screen is where we can change the control variables and change screens, and we can change the set point. The tuning screen cannot be accessed without first putting in a password to protect from unauthorized changes. The GeoHeater SCADA, unlike the GeoPrinter, connects directly to Ignition. It allows for precise monitoring of data from remotely, whereas on the HMI, you have to be directly at the system to control the variables. The GeoHeater SCADA screen allows remotely to see the PWM, set point temperature, the current temperature, as well as the status of the heater.
So for testing validation process, for the GeoPrinter, we had the Marlin G-code testing. We wanted to make sure that our Y-axis was because two-stepper motors means you have to sync them together, as well as editing the G code and adding the Y-axis code to the G code. For the GeoHeater testing and validation, we did small batch testing, anywhere between 1 to 3 kilograms. But for this one, we used 2 kilograms. We wanted to make sure it had a 1 degree offset, as well as 50 degrees Celsius max after about 1 hour. For our overall challenges, we had development and testing. For the development stage, we had the Y-axis motors synchronization issues. We had the Marolla code editing and implementation, as well as the SCADA communication stuff. For the testing, it was the geopolymer mixture calculation limitations that we had, as well as the tuning of the heater and the geopolymer getting cured and stuck inside of our auger system.
Now talking about our testing results for a GeoPrinter, we're able to synchronize our Y-axis motors for our Y platform movement, and we were able to make a G code file to be able to print 2 lines of geopolymer on top of our Y-axis platform. For the GeoHeater, with a set point of 30 degrees Celsius, we managed to reach our set point with minimum overshoot and a 1 degree Celsius of steady state air. Next, we have a video summary.
There is supposed to be music, but it's fine. So we have fly ash and sand mixed already together, and I'm incorporating the sodium SL kit. This is the first part of our alkaline activator, and then we add in also some sodium hydroxide, and this will finish activating it. You can see it'll start clumping together. This is like a gel that kind of binds all the aggregates. And then we will dilute this with water. This will start to turn the geopolymer a sort of darker color, and it gives off some fumes, so we have to rotary spray this to mix this. We add enough water so that it becomes liquid enough so we can actually print it and the auger can flow through the system. So here you'll see the GeoPrinter. We're putting the geopolymer through the top funnel right there, and an auger will bring the geopolymer down, and it's curing it through those 2 plates over there. The printer moves quite slowly, so this also sped up. And then you can see the Z-axis moves the entire extruder up and over, so we can start printing the second line here. And then after this clip, it'll show a side-by-side of the previous function of the GeoPrinter. As you can see, the geopolymer kind of just spreads out. It's way too liquid and it doesn't cure properly. But here you can see this second line that we're printing. It's much thicker and it holds its form, and it's actually curing. So now, here's some videos of the GeoHeater's function. You can see a wiring diagram right there, and we'll open up the control cabinet right here to show you what it looks like inside. It's got an Ethernet switch, a 24-volt power supply, and a PLC. Here you can see the SCADA. We're doing one of our small batch tests right now. And then this is also one of the other functions you can do with the GeoMixer. You can make a large batch in this. This is the original function of the GeoHeater. We also use the GeoHeater to cure geopolymer on the bed of the 3D printer. And so you can see the SCADA here. The set point temperature is set to 33 degrees Celsius, and the current temperature is rising up to meet that. It'll fall just under 33 at 32 degrees, but it stays consistent throughout the entire run. And this is conducted over around 7 minutes. Here's a picture of us curing geopolymer that's already on the printing bed, and then here's a picture of one of our small batch tests to ensure that our PI goes to properly. And the maximum temperature is around 50 degrees Celsius. So for potential future projects, a future team could implement some of these ideas. Rotating heating nozzle, where you could print more complicated shapes such as circles or squares, as we can only actually print 2 lines due to the 2 copper plates facing the same way. pump-fed GPC extrusion, so that an operator doesn't actually have to pour in geopolymer and stand there the entire time. Upgraded motor system for the auger and all the axes to support more firm geopolymer and also support more load on the actual printing bed. An isolated enclosure for the GeoHeater. This would ensure like a higher maximum temperature and faster curing. And then perfecting the GPC mix, as this is all a work in progress, and we're all still trying to figure out the exact mix that would work the best to print vertically. Yes, ma'am. So here's our parts list. The total came to around $700, and we had $12,000 of room because our budget was around $2,000. Thank you to Dr. Alam and Professor Theos and our grad student, Gordon. Thank you. Any questions?
Did you have any issues with your auger breaking or your motor tripping?
Yes. It actually broke 4 times, and we had to reprint it many times. We changed the material it was actually made of, because when we originally got it, it was just made of PLA plastic. Now it's made of like a nylon kind of material.
Yeah, ranges from PLA plus to nylon based material.
We also had some trouble with the y-axis coming off the bearings, so we had to deal with that a couple times too.
So again, as I told the previous group, I'm not the sharpest tool in the shed. I thought I heard y'all say something about voltage maybe and going through that process.
Mm-hmm.
So how long did it take you to get the appropriate voltage to get the quality results you needed? Was it a one-shot deal, or did you have to do it like 20 times, 8 times?
So in order to do the testing for the geopolymer, we started around 5 volts and then we slowly increased it because you can increase it while it's printing. So we noticed that 5 volts wasn't quite doing it, 10 volts wasn't doing it, 15 was somewhat getting it there, and we turned it to 20, it was doing it pretty good. We turned it to 25 and we realized that it was starting to smoke and starting to burn. So we then quickly did it back to 20, and that's what we set it at, and that's what it worked at.
That's our sweet spot for the speed we're actually putting at. If we were to change the speed or upgrade the motors, this would have to be found again, the correct voltage to carry.
It also depends on like the consistency of the geopolymer, finding that sweet spot, water to chemical ratio, and then that's when we did the testing to increase the voltage, because sometimes it came out too quickly based off the previous Capstone project. Finding that right area, right measurements, and the right voltage. That's what we found have the best foundation as possible.
So working with your voltages then, it didn't impact your budget that much?
No, the transformer was already supplied from the previous group that worked on this. And so we never had problems with any fuse blowing or anything like that. So we had the exact same materials for that part.
Thank you.
After doing a run of printing, was there like an extensive flush
Yes.
cleaning process?
Very much.
Yeah.
On this slide right here, you can see this is one of the times where the geopolymer would actually cure inside of the PVC housing, and that picture on the right shows the geopolymer like stuck to the auger.
Yeah.
And so in these cases, we would take gloves and a paper towel, and we would kind of try to get most of it off into a bucket, and then we would dilute it with a ton of water, and then we would just dose it correctly.
And actually, the first time we did this is when the auger broke, because the stress on the coupler to the auger system was like very, very small. So the geopolymer still came. So as we were cleaning it, we snapped out. So we had to start doing different things.
During the cleaning process?
Yes.
How many GPC mixtures did y'all do for you guys final product?
It normally varied every time we did a run, and this would just mostly be a variation of how much water we were adding. We did around, I would say like 10 runs total of printing, and we found the correct water ratio around our 5th or 6th run. And then it was just a matter of trying to find the correct voltage, getting it to print consistently too. Because if you saw in the video, there was that first line, it kind of stopped and it got stuck, and we had to
of temp.
Yeah, we had to move the auger around a little bit to get all the geopolymer through.
So, I know this wasn't entirely your fault, the mixture and stuff.
Mhm.
Obviously, that's the obvious thing at the end, but did y'all work at all with the civil engineering students to try to even fix that problem? Or did y'all run out of time?
So, Stephen Gordon, our grad student, he normally teaches this kind of stuff, and he's very knowledgeable about GPC. And he taught me what he knew and like what he gave me the mix. But the exact mix that he gave me was way too firm, and the auger couldn't push it through. So we had to go the route of diluting it with more water to be able to actually print them. And one of the main reasons why we made the GeoHeater in the first place was because we saw that video where the geopolymer was kind of cooling out of the extrusion. So we wanted to halfway cure it originally. That was the original idea. And then we realized, well, we can also just dilute it with water, but that affects the tensile strength of it, and it's kind of a whole balancing act of all these
Right.
factors.
To find the new Roman concrete.
Yeah.
Did y'all do any so I saw like the print head, the thing that I'm guessing would actually like finally cure and heated that cement.
Yeah.
It was just two plates side by side, correct? Or if I'm not wrong. Did y'all ever like experiment or research or other types of print heads for that? So like different like setups of plates or another form of
That idea was tossed around a couple of times. One of the main things was a motor that drive, like it can follow the rotation of like whatever you're printing. Because we realized if you were to do something that's more like a square, it wouldn't exactly induce ohmic heating properly. So we would have to have the two plates actually move along with it. But that was too much to do, like because we already had the y-axis and all those problems that came with it, and editing the firmware. So we ended up just suggesting that someone else, whoever works on this project next, can do that.
Yeah, we spoke with our sponsor, and he pushed us in the direction of focusing more on the control aspects of this entire thing rather than the nozzle itself.
Yeah. Oh. Any other questions?
I may have missed this. I didn't walk in really late. I apologize. But can you guys explain what GPC is?
Yeah.
The difference between that and regular cement?
So geopolymer concrete does not use cement like regular concrete, and so this geopolymer that we're using in particular is using sand and fly ash. And fly ash is a byproduct of burning coal. This is also environmentally friendly because we're taking fly ash out of the environment because it doesn't degrade, like it stays in the environment forever. So using fly ash and sand as an aggregate, which is basically just filling up the space. And then we have something called an alkaline activator, which will become like a gel, and it binds all this together. So it's in a form it is concrete, but it doesn't use cement like concrete.
We also introduced a new chemical that's plasticized with cyclical water bonds out of the geopolymer. So what we found out after that printing is left that white ash on it.
Yeah.
It might be a little bit too dangerous.
That was something that Dr. Alam wanted to experiment with. So we tried that for a couple of runs, and we realized it wasn't exactly perfect for printing. So. Any other questions?
Thank you.